Other sample problem, 23.04. So it says, what is the net charge enclosed by the Gaussian cube of sample problem 23.02? Okay, so actually in 23.02 we have already calculated some of the total charge for different surface. For example, the left surface, the right surface, and also the top surface, which are -12, 36, and 16 Newton meter square per coulomb. Okay, so actually it asks you the net charge. Okay, so it asks you the net charge, and of course we need to use the Gauss law. Okay, so for the Gauss law, you can simply consider that the phi or I should say, when you need to use the Gauss law, you need to find the net flux for the whole cube. So as long as we have calculated 3 of them, we need to also calculate the remaining 3 surface. So for the left, right, and top, okay, so we still need to calculate the front, and then the back, and then also the bottom. Okay, so a quick observation is that it is clear that 5 front and 5 this one should be black. This one should be back. Okay, so this one is 5 front, means this one is the front. This one is the front, and as long as this E have this expression, okay, so it only has a x-axis component, y-axis component. It doesn't have any z-axis component. And actually, for this front surface, the dA actually is pointing to the positive z direction. So it is something like dA times k hat. Okay, so if you consider E dot dA, it would be clearly 0. And similarly for the back, okay, it would be something like similar. For the back, the dA will be like negative dA k hat, something like that. So E dot dA is also 0. So we can quickly observe that these two are 0. So the remaining one is the phi bottom. We need to calculate. Okay, for the phi bottom, it would be integration of B E dot dA. Okay, so for the bottom, the dA will be like the right side is the x-axis, positive x-axis. This one is positive y-axis. Okay, so for the bottom surface, dA will be negative dA negative dA j hat. Okay, so for E dot dA will be 3x I hat 3xi hat plus 4j hat, and then dotted with negative dA j hat. Okay, so I hat dot j hat will be 0, j hat dot j hat will be 1, so it turns out to be negative 4 dA. Okay, so here will be something like this, negative 4 dA, and then for the bottom surface. And then okay, so for the surface area, this is x equal to 3 meter, x equal to 1 meter. So the length of the square will be I mean the length of a side of the square will be 2, so the surface area will be 2 squared. So it will be -4 times 2 squared will be -16 n nm squared over c. Okay, so the total, I mean the net thrust will be add 1, 2, 3, 4 together. Okay, so it will be -12 plus 36 plus 16 and then -16. Okay, so it will be, okay, 16, -16 cancel. So these two add together will be 24 nm squared over c. Okay, so making use of the Gauss law, we can have Q enclosed equals phi over epsilon naught. Sorry, should be epsilon naught times phi. Epsilon naught times phi. Should be something like that. Okay, so it will be equal to 8.85 times 10 to the -12, and then times 24. So it will be 2.1 times 10 to the -10 coulomb. Or if you would like to use the scientific prefix, it will be 210 picocoulomb. Okay, so pico is 10 to the -12. So you need to convert it a bit. Okay, put 2 zeros to the front. Okay, it turns out to be 10 to the -12. So this is a pico. So far any questions? Okay, so here we'll talk about charge isolated conductor. Okay, so here is a highlight. It says if an excess charge is placed on an isolated conductor, that amount of charge will move entirely to the surface of the conductor. None of the excess charge will be found within the body of the conductor. Okay, so this is a very important characteristic. Characteristic. 就是中文意思就是说，有一个固体的话，它所有电荷都会跑到它的表面啊。如果里面有空腔的话，也会跑到那个空腔的那个表面啊。但是如果它一整块的话，它就会全部都跑到表面去，它不会在那个导体的里面去分布啊。因为它的意思是说，如果你有一个固体，你中间有电荷的话，那比如说中间有一个 Q 的话，那我任意画一个高斯面，它会 enclose 一些 charge 嘛，所以你按照那个高斯定律的话，它就会有电场，那有电场的话，就会把这个 Q 推到边上去啊，那直到它跑到边上，它就不能再往外跑了，所以它就会跑到边上作为一个平衡的状态。所以你任意在一个导体里面画那个高斯面，它应该没有电荷，也就不应该有那个电场。这个是一个特性，就是。So it means that inside a piece of conductor, piece of conductor, conductor. Okay, E will be 0, and then also no charge. Okay, no charge inside. 就是有这两个特性，全部电荷都会跑到表面的地方。To go to the surface. So yeah, so this is what the highlight means. Okay, so here we will consider the conductor. Okay, so okay, so here we assume we have a very large conductor, very large conductor, and we assume a closed cylindrical Gaussian surface， 就是一个封闭的一个圆柱形的高斯面啊。A closed cylindrical Gaussian surface embedded perpendicular in the conductor enclose some of the charge. OK， 他说它跟它垂直的意思是，你这个圆柱体的话有一个轴心，就是一个圆柱形的话，就是你把所有切面的圆心连成那个轴啊，那个轴跟这个平面垂直啊，是这个意思。So electric field lines pierce the external end cap of the cylinder, but not the internal end cap. The external end cap has an area, and the area A. Okay. So here we define a cylindrical Gaussian surface like this. Half of it is inside the conductor, and then half of it is outside. And as I mentioned just now, inside the conductor there won't be any E field, so we don't need to consider the E dot dA inside the conductor. So the remaining part is the orange part. We need to consider the net flux at that part. Okay, so actually, as long as this conductor is very large, okay, for this, so for the E field will be also perpendicular to the surface, as they are symmetric. So in such a way, for the side of the cylinder, there won't be any E dot dA, because the dA will be something like this. The dA will be something like this. They will be all the way perpendicular to the E field. So in such a way, E dot dA will be a zero. So we only need to consider. So we only need to consider this surface. We only need to consider this surface. Okay, so here we try to consider the figure like this. Okay, we try to rotate it a bit. Okay, so actually this is the surface. This orange one is this one, but if you turn to a suitable angle, then this side you only see a line here. You only see a line here, and actually all the E field are perpendicular to this surface. Okay, so in such a way, the dA or the A vector is also parallel to the E field. Okay, so here so this is the left side of the Gauss law. And as long as we assume that the E field will be uniform according to the symmetry, and E and A will also be parallel to each other, or actually pointing to the same side. So this thing turns out to be E times A. E times A. Okay. So E dot dA will be E times dA, and then E is uniform, so it will be. Turns out to be the uniform E times the area of this circle. Okay, so it turns out to be like this: epsilon r times EA equals Q enclosed. Q enclosed is the charge enclosed by this cylindrical Gaussian surface, and then we assume the surface charge density is sigma as before, okay, and then times the cross-section area. Okay, so this circle and this circle will share the same area, so we use the letter A for that. So here we can simply cancel. We can simply consider this side, and then cancel this A and this A. So it turns out to be E equals sigma over epsilon naught. Okay, sigma over epsilon naught. Okay, like this. Okay, very quick. So if you still remember, in chapter 22, we try to calculate the E field generated by this disk. At that time, we just assume this is a circle. It's a circle disk, and then it turns out the E field at this z-axis will look like this. And then finally, we assume that this R is infinitely large. Okay, just like this case. And it turns out the E will be like that. Okay, and then you will say here's a 1/2 factor here. Okay, a 1/2 factor here. The idea here is that we only have a disk here, so it will generate the E field both upside and pointing to the bottom. Okay, so each side will take the half of it. So it turns out to be sigma over 2 epsilon naught. But here we assume that this conductor is very, very large. Okay, not only to the top and bottom, but also to the left side, going infinitely far away. So in such a way, all the E field generated will point to the right side. So here it will be 2 times larger. Okay, but but here to record this is just to let you know that in chapter 22 we don't use the Gauss law, and then we try to separate this into many small parts, and then try to find the dE for each small part, and then finally maybe we need to do some cancellation, and then finally do the integration to add all of them together. So the steps will be there will be more steps to come up with this expression. Okay, but we don't need to know the Gauss law. Here in chapter 23, what we have learned is the Gauss law. So it consists of surface integral. Okay, which will be a difficult part for the mathematics, but by making use of that mathematical tool, we can have a quick steps to come up with this solution. Okay, so the idea is something like this. Okay, so for here we have another sample problem, 23.05. So we just quickly go through that. So it says the figure A shows a cross-section of a spherical metal shell of inner radius R. Okay, so from here to here is the inner radius, 就是内半径. A point charge of -5 microcoulomb is located at the distance R over 2 from the center of the shell. Okay, so it is not at the center. Okay, if the shell is electrically neutral, what are the induced charge on its inner and outer surface? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay, so yeah, okay, so the first step is to assume a Gaussian surface to be inside this shell. Okay, 就是在壳的中间定义一个球形的一个高斯面。Okay, so the idea for that is because this shell is conductor. This shell is a conductor. Where is this conductor? Yeah, it's a metal shell, so it's a conductor. So as I mentioned, inside the conductor, the E field should always be 0. So in such a way, for this Gaussian surface, we apply the Gauss law. If we apply the Gauss law for this Gaussian surface, then this net flux will be 0. The net flux will be 0. So as epsilon naught times this net flux. So it will be equal to Q enclosed, which means that the Q enclosed by this Gaussian surface will be 0. So it means that as much as we have a negative charge here, negative 5 microcoulomb. Okay, so for the inside surface of this sphere, of this shell, there will be induced charge. Okay, that will be positive 5 microcoulomb charge on the inner surface, And actually, the shell is electrically neutral, which means the total charge on this shell will be 0. So here we have some induced charge, positive 5 microcoulomb on the inner surface, which means that there should be negative 5 microcoulomb charge on the outer surface. Okay, so the idea is something like that. So we can determine the inner and outer, the induced charge on the inner and outer surfaces. And then the remaining question asks you, are the charge uniformly distributed, and what is the field pattern inside and outside the shell? So it is not easy to explain. The simple idea is that as much as this charge is close to the left side, so the positive charge will be somehow attracted by it. Okay, so there will be more positive charge focused on the left side, for the inner surface, and then this part will be denser, and then this part will be sparser. So so this is only true for the inner surface, and then it tells you that the electric field line will be something like this. So okay, so actually it's hard to explain. Okay, so basically it's due to the computer simulation. So it's not it's not easy to explain why is this curvature like this, but but the key point here is that for the outer surface, the charge will distribute quite uniformly, and then for the outside part, the E field will be like all the way pointing to the center. It feels like if you just observe, if you just standing outside to observe this E field, it feels like the charge is actually, there's only one charge at the center of the sphere. 所以这里的重点是，类表面的话就不重要，就是它正电荷就比较是接近左边的表面，但是在外表面的话，就是负电荷会比较会很均匀的分布。然后你从外面看起来的话，它就像这个东西全部拿掉，就像单纯一颗电荷在这个球的正中心的位置。但你说现在的话，它不是在正中心的位置，但是它外面加了一个球壳，你在外面看到的话，就像是那个电荷在正中心的位置。这个我们叫做 shielding。We call this one a shielding effect. Shielding 就是有一个金属的壳包围着之后你在外面看到的东西就是会被屏蔽掉，有点像一个微波炉这样，它就是在门或者是六个表面都会有金属包围着，你外面看到的跟里面看到的就不一样。 Okay, so here we have another part about the how to apply the Gauss law for different structure. Okay, so for the first one is the cylindrical symmetry. 这个叫做圆柱的对称啊，圆柱的对称。Okay, so here it says a section of an infinitely long cylindrical plastic rod with a uniform charge density lambda. Okay, so the main point here is this is a plastic rod, which means it's an insulator. And then it is also infinitely long. And then with uniform charge density, lambda. Okay, so the charge distribution and the field have cylindrical symmetry. So to find the field at radius r means, you try to find a point here, and then you try to draw a perpendicular line to this rod. Okay, so this distance will be an r. Okay, so to find the field at radius r, we enclose a section of the rod with a concentric Gaussian cylinder of the radius r and height h. 所以它这里是说，这个是圆柱形的，那我们也定义另外一个圆柱形的高斯面，但是跟它是 concentric 是同心的，同心或者是同轴的意思，就是那个轴是一样，或者是圆心在同一个位，同一个轴上面。Okay, so with radius r, radius small r, and height of h. The height of h. The height doesn't really matter because finally this h will cancel out. So the net flux through the cylinder from Gauss law reduced to something like this. Okay, so of course at the very beginning we can try to write out the Gauss law to see how it can apply. Okay, so here as long as this is a rod with a charge, and then it is infinitely long. Okay, so actually the E field generated by this will be like also pointing from the rod to a horizontal direction. Okay, and then also go through the radius. Okay, 就是径向的 radial distance, radial direction. 就径向的方向 Okay, so in such a way, for this Gaussian surface, for the top face and the bottom face, there won't be any. It won't contribute to the net flux. So only the side of this cylinder will contribute to the net flux, and so we can simply imagine that E and dA actually points to the same direction for different point on the side of this cylinder. So in this case, this E dot dA will turns out to be E times dA, and then finally it turns out to be E times the surface area. Okay, so finally it turns out to be something like this. This phi is actually this surface integral, and this phi turns out to be E times dA. Okay, so what is the surface area of the side of this cylinder? Okay, so we can just try to cut it and then flatten it. Okay, if we try to cut it out and then flatten it like this, so it turns out the height will be h, and then the width will be like a 2 pi r. The width will be 2 pi r. So if you try to cut this cylinder and then flatten it, okay, of course this one will be the width of this rectangle. Okay, so this area will be nothing but 2 pi RH, 2 pi RH. So this is actually this one. And then finally, we can cancel this H with this H. So we only leave E on the left side and then put all the variable on the right side. So finally, it turns out that E will be equal to lambda over 2 pi epsilon naught R. Lambda over 2 pi epsilon naught R. So it will be E, it will be an E field. Okay, E field will be like, it will be related to the distance, inversely proportional to the R, inversely proportional to the R. And actually for this part is a constant for a specific case. Okay. So any questions? Okay. Okay, so this is an other case, similar to the several pages before. Okay, but here we have a non-conducting sheet. So it says a portion of a thin infinite non-conducting sheet. Okay, so the difference is here we have a thin, okay, infinitely thin, okay, 就是它一点厚度都没有的。With a uniform positive surface charge density lambda sigma. This one should be sigma, and a sheet of thin plastic wrap uniformly charged on one side can serve a simple model. Here apply the Gauss law. Okay, so here is the thin infinitely large non-conducting sheet. And then here, similarly, we try to apply. So we try to assume that there is a cylindrical Gaussian surface here. And here, okay, so here is the sheet, but yeah, it should be very, very thin. So we only have a charge. We only have a charge on one side. So although it, I don't think it draw in a good way, but actually you try to consider it's very thin. So we only have one row of a charge there, because all the charges, should be aligned like that. Okay, so here we try to apply the Gauss law for this Gaussian surface, and just as what we explained before, for the side of the Gaussian surface, it won't contribute to the net flux. It won't contribute to the net flux. Only this side and this side will contribute to the net flux, because this infinitely large sheet will generate E field pointing to the left side for the left side, and then pointing to the E field pointing to the right side on the right side. So so these two top and bottom surface will contribute to the net flux. Okay, so in such a way, this E dot dA will be EA plus EA, okay? So one EA on the left side, one EA on the right side. So, and then this Q enclosed, similar to previous case. For this one, we have sigma times A. Sigma is the surface charge density. Okay, and here finally we can cancel all the A. This A can be cancelled. So finally, E equals sigma over 2 epsilon naught. Okay, just as just as what we derived before. Okay, just as what we derived before. Okay, here we also assume that this is infinitely large. Okay, so if this is infinitely large, it will be actually the same as this one. Although you try to draw it as a rectangle, but yeah, as long as it is infinitely large, then whether it's circle or rectangle, it doesn't really matter. And then it turns out that this one and that one will have the same expression. Because in this case, it is spin, it will generate E field on both left side and right side. So each side take half of the E field. Okay, so here, this 1/2 vector will be the same. Okay, so here we try to mention that we use different ways to find the E field generated by the same structure, and then with the same conclusion. But two methods will have different complexity for computation. Okay, so here we try to have two conducting plate placing close together. Okay, so this structure is important. We will come back to this structure in chapter 25, which is actually the capacitor. Okay, so here it says we have a cross-section of an infinite conducting plate with excess positive charge. Okay, so this one we have a conducting plate with positive charge, and then for B we have identical plate, 一样的, and then with excess negative charge. Okay, we have negative charge for B. Okay, so far we try to consider these two are independent. Okay, you try to consider we have a case like that, and then we have another case like that. So just as what we derived before, this surface will generate E plus on both sides with a sigma 1. Okay, originally we consider there are two surfaces, the left surface and right surface, both with sigma 1 to be the surface charge density. So the E plus will be sigma 1 over 2 epsilon naught. And then similarly, for this case, just forget this one at this moment. So if you only have a infinitely large surface with a negative charge with the same surface charge density, but with opposite side. Okay, so the E minus will be actually the same value, but here for this case, the E field will point to the left side on the left side, and then point to the right side on the right side, point to the right side on the right side. And then for this one, the E field will point to the right side on the left side, and then point to the left side on the right side. So far we consider these two are independent cases. So for the third case, we try to put these two together. Okay, put these two together with a distance. Okay, this distance doesn't really matter at this moment. But after we place them close together, the positive charge and the negative charge will attract each other. So all the positive charge will go to the right surface, and then all the negative charge will go to the left surface. In such a way, the E plus will be 2 sigma 1 over 2 epsilon naught pointing to the right side, and then the left side will be somehow like 0. You can also consider it's like you try to ignore this one, and then you try to add these two cases together. Okay, so there will be 3 regions. Okay, the region 1, region 2, and region 3. Okay, so for the region 1, for the region 1, it is the left side to this one, so it's pointing to the left side, and then it will be also the left side for this surface. So the E field generated by it will point to the right side. So they have the same value, but will point to the opposite side, so they cancel each other for this region 1. But for the region 2, this one point to the right side, this one also point to the right side, so they end up together. Okay, so in this case, in the middle, so the E field is somehow like double. Okay, and for the right side, okay, it is the right side to this one, and then also the right side to this one. So this one will point to the right side, and then this one point to the left side. So for the region 3, this one and this one cancel each other. Okay, so we will find that E equals 0. E equals 0 for region 1 and region 3, which means outside of these two surfaces. But here we will consider all the charge will go to the inside surface. So which means that we will have a 2 sigma 1 for the surface charge density. And here we try to define a new surface charge density as sigma rather than sigma 1. So here we just assume that this sigma is 2 times of sigma 1 as the new surface charge density. So finally we have E equals E plus E minus, and then we will have so it will be E equals sigma over epsilon naught. So it means that it tells you if you have two conducting plate with same amount of charge with opposite side placing close together, it will generate a uniform E field. Between them. The direction will be start from the positive plate pointing to the negative plate. Okay, so this is the most important point you need to keep in mind.